All right, hello, mathematicians. We are live. This Chapter 3 test webinar. I'm just going to check to see who's signed into the Google Doc and who has clicked on the link to view. So it looks like two people have joined us for the link, but I see a lot of names on the Google Doc. So if you're here, just sign in on the Google Doc and then make sure you click the link to access the video, since we're going to use both of those. You should be seeing a presentation slide that says Chapter 3 test webinar, and then just say yes if you can hear me on the audio. All right, thanks Carolyn. Hello. More people are signing in. Thank you, Olivia. And don't forget to give a greeting. Hi, Julia. Okay, looks like Justin is here. People are picking their colors. We'll just wait like one more minute and then we'll get started with the slide presentation. It'll just be about 5 minutes, maybe 10 at the most, and then I'll take your questions from anything having to do with Chapter 3 as we prepare for this test. All right. Hi, says Olivia. Hola, says Carolyn. Oh, where is Dr. Carenti, says Julia. So, for those of you who don't know, that's my wife, Mrs. DeRosa. She's also Dr. Carenti, an optometrist. She's not gonna. I don't think she's gonna join us, Julia, for this webinar, but maybe she can say hi at the end. Hello, says Justin. Ooh, ciao, says Andrea, a little Italian. And Harshal is here. And Nick doesn't have anything to say. Hello, Alex. All right, CK is psyched for math. So let's get started, and then we will take questions. So how this is going to work, I'm going to present on the slides, and then you can actually start typing questions whenever on the second page of this Google Doc. So there's a second page, and I showed how to format a question. And then after I'm done with the slide presentation, I'll look at those questions and just take them in order until about 7:45. We'll see if there's any last minute questions, and we can go from there. All right, so let's get started. Chapter 3 test. I'm going to start the presentation. All right. So first of all, you got to know the test format and rules because it's our first non-calculator and calculator test. So I'm going to give you both parts. You're going to get the whole test initially, and then you can work on the non-calculator section. You can even work on the calculator section. But the rule is going to be when you decide you want to use your calculator, then you have to surrender part one. You have to turn in the no calculator section to the bin, and then you can take out your calculator. Now, the calculator section is three open-ended questions, but even some of those can be done without a calculator. But there's a few. There's at least one where you want to do a derivative at a particular point, or it's kind of a weird function that you want to calculate. So you want to use a calculator for that. But most of the tests can be done without a calculator. Okay, then some test emphases. There are obviously the four representations that you got to know. So this is basically AP Calc. For every unit that we do, limits, derivatives, integrals, and series, you want to have an understanding of the graphical aspect, the algebraic and analytic aspect, the numerical or tabular approach, and then a verbal approach. So I just kind of listed some of the key skills under each of those that you need to know. And I'll post these slides up on Classroom after the presentation is over as well. But for graphing, you want to know matching f and f prime and how to graph a function. Analytically, you want to be able to compute derivatives with the rules. You want to know differentiability and continuity, those definitions. And it's possible you need to know the definition of a derivative as well. Table problems, we did do a couple in class where you had to compute derivatives based on a chart. And then verbally, you might have to justify differentiability or not. You might have to justify horizontal tangents. You might have to explain a matching question, things of that sort. Here's a quick tip on differentiability versus continuity. So, yes, you should know the limit definitions for both of these. You should be able to write those down. But these are some quick informal notations that will be helpful to you. So, or not notations, but just descriptions. If a function is continuous, if you remember the idea of it being connected or traceable, it has no holes in it, no asymptotes. That's what means. That's what it means to be continuous in an informal sense. Obviously, there's the limit definition, but this is just a helpful trick to remember. And then differentiable, that's associated with smoothness. If a function has smooth curves, then it's going to be differentiable at those points. I'm just going to double check. Yes, everything is working. Okay, hang on one second. Are you able to see when the slides change? Just tell me if you can see what the slides changed. You can type right in the greeting box. Quick question: can you see when the slides are changing? As I was just going through that, can you see when they change, or do the slides not change? Yes. Okay. Just want to double check because sometimes when I do this, it could be wrong. All right. So a couple more slides. Calculator section, some tips. What do you need to be able to do on the calculator section? So you want to be able to graph a function, in the y equals, and then show it on the screen. You might have to compute the derivative at any point. For the 89 and the Inspire, it's different, but for the 84, it's going to be Math 8. Okay, Math 8 is the button you click, and you type in the function and the point you want to compute the derivative. You might also need to use the calculator to locate a horizontal tangent line. Andrea mentioned that in class. You could do that by finding the peaks or the maximums and minimums on various intervals, or even the zeros of a function. You want to be able to find that with a calculator as well. So both of those are in play for use of the calculator. Non-calculator section, I would say, the main things, what do you need to be able to do? Obviously, take a bunch of derivatives. You got to be able to compute derivatives with rules. Got to be able to do them from tables, and you got to know when something is differentiable or not. All those cases. Um, I'm sorry, this second bullet point shouldn't be here. That was for the calculator section. You don't need to use the T84 on the non-calculator. What else is important to know? So there's definitely one question. I think, yeah, at least one question. I think one question on particle motion on an axis, arbitrary axis. We use S of t for position. It's like the similar, could be similar to our 3.4 example that we looked at in class. We also looked at one in 3.5 with trig. And you might have to know that position can be, you take the derivative, you get velocity, you take the derivative, you get acceleration. Could have defined the average velocity on an interval or the instantaneous velocity at a particular time. You might even need to find, the speed or when something is speeding up. And you may need to use a graph to judge whether something is moving in the positive direction or negative direction. So all that's in motion or in that's fair game for tomorrow's test. There could be a problem on particle motion. All right, so thanks for watching. I know that was just a quick run through of some important tips or things to know as we prepare. And now we're going to get to your questions. So let's see what people are saying. And feel free to jump in and answer each other's questions if you'd like. Oh, I'm going to answer my question. And I'll try to type these up, but if I just say it out loud, then I can go back later and fix it. But this was yes. Sine of x is differentiable everywhere because it's always smooth. Well, here's a good question from Andrea and CK. What are other functions that have discontinuities? For example, y equals 1 over x. So if you have to give an example of a function with a discontinuity, I'll just give you a couple examples. You could have a step function. You could have functions with a jump. You can define your own, piecewise functions that you create that have discontinuities. And then obviously the most famous are rational functions, which have different kinds of asymptotes. So you have a rational function where the denominator factors with, a couple of factors, and then that'll give you a few asymptotes. So there's just examples of functions that have discontinuities. Now, I will note though, the way you're asking this question is a little bit odd because you're saying, what are other continuous functions that have discontinuities? So, is actually this could be a pretty technical point that you're making because the function 1 over x is considered a continuous function in the sense of being continuous in general. But then maybe you're saying, does it have but technically it does have some discontinuities on negative infinity, comma, positive infinity as the interval, or somewhere on the real numbers. Maybe that's what you're asking. Either way, I think my examples could work for both. But yeah, that was that technical definition of continuous, where 1 over x is continuous in general, but it's not continuous on all the real numbers. Okay, here we have a question, but no hyphen. I'm sorry. Please follow the format. I need a hyphen. I need to know who asked the question. That would be helpful. Okay. Thanks, Julia. How do you find the derivative using the limit definition? Okay. So this is for this, you want to look back to, if you want to pick up a particular problem, we can look at it, but I would say look at homework from 3.1 to 3.2. And I like if we're given a choice, I like the H definition. And basically you just plug in x plus h in the function. Whatever the function is, you plug in x plus h, you subtract f of x, and then you're going to have to do good algebra to get it so the function, so the inside the limit, we don't have an indeterminate form. So usually that might mean factoring, it might mean multiplying by the conjugate, it might mean simplifying a complex fraction, but basically do good algebra until the limit can be calculated. Usually that h in the denominator is going to cancel out somehow. That's how you use the limit definition. If you want more details or you want to put another example down towards the bottom, that would be fine. How to do derivatives on the Inspire? Nick, and for CK, Andrea's question, maybe they mean functions that are continuous but not continuous at every point. Well, every point of their domain or every point of the real numbers would be the real distinction we're going to draw there. If you mean every point of their domain, then that would be what we're talking about, continuous in general. If you mean every point of the real numbers, yeah, every point of the domain. Okay, that makes sense. Yeah, I think that might have been what they were talking about. How to do derivatives on the Inspire. So you want to go to the menu, and then calculus, then derivatives, and it should populate on the screen. Practice with it so you're not doing it for the first time on the test. All right, Harshal wants to talk about study guide 3A, comma 3E. All right, I think I can pull those up for you. So you should be seeing my sketch pad now. Partial, do you see the sketch pad? I'm going to draw in here to answer some questions. We have to draw, so just let me know if you can see that on the screen. And we're going to pull up 3E. Okay, thank you. Yes, you can see it. Great. Okay, 3A and E. Okay. Yeah, these are challenging questions, but I like them. I'd say A is particularly challenging. I provide a really detailed answer on the answer key, so I would follow my work there. But what ends up happening is, this expression, it looks a little bit suspicious, and it's not obvious, especially if you're working with limit definitions for the first time. But you can rewrite this expression into essentially two limit definitions. So it ends up you break this up, and the trick is h is the same as 0 plus h, and negative h is the same as 0 minus h. So you can break up this fraction into two fractions over h. And what you end up having is the limit definition, sorry, two fractions over h. You end up with the limit definition of the derivative twice. And you can factor out a 1/2, so it's over h, and then it works. And so you have the limit definition plus this one, two limit definitions added together equals 0. And then what you can do is move one to the other side of the equation. And what it essentially shows is that the limit as we're approaching from the left is equal to the limit as we're approaching from the right, which means that the derivative exists. Okay, it's pretty complex. I know that was a quick answer, but I give a lot more detail on the answer key. So Harshal, look back at the answer key and then feel free to ask that again. But that one I agree. This one is the hardest. As far as analytically, you really got to get into the definition, and it's not obvious. You have to rewrite this in a different form. As far as 3e is concerned, here's the key idea. If f of x is differentiable at 1, that means that the slopes from the left have to match the slopes from the right, or the derivative from the left has to match the derivative from the right. So I take the derivative of the left expression, which is this one, 2ax minus 1, and the derivative of the right expression, which is this one, ends up being b plus, and then this is cx to the negative 1. Yeah, so it is negative 1x to the negative 2. Or there should be a c there. And so anyway, the idea is that these two functions can never be, these are not going to match. Okay, for any value of a or c or b that you pick, if you pick constants, this one's linear, and this one has an x squared term in a denominator. Excuse me. So since the function or the derivative from the left doesn't match the derivative from the right, it's not possible to find constants where it's differentiable. Okay. We are going along with these questions. Good questions. So Harshal, again, 3a, check my answer key, and 3e, explained. Okay, Olivia is asking, can't the constants be found using b plus c equals 2 and the other two equations? Okay, that's a good question, Olivia. I think you might be thinking of continuity. So let me answer it this way. Yes, you can find constants to make it continuous. You can make the graph both meet at the point 2, but the derivatives will not match from the left and from the right. They're fundamentally tied up with different types of functions. The derivative of this one on the left is a linear function, and the derivative of this one down here is, it's a rational function. And so since the derivatives cannot match from the left and from the right, we can say that it's not possible to find constants where it's differentiable. Okay. Yeah, good question, Harshal. How do you know what a graph looks like for equations such as x to the 1/3 or x to the 5/6? All right, x to the 1/3 is a parent function. You just have to know is that's a cube root function, which is the inverse of a cubic. So for that one, you reflect a cubic function, which you should know, over the line y equals x. For x to the 5/6, something like that graphically. Let's see how we can think about that. Well, if you have a sixth root, it is going to be positive. So we know it's not going to go below the axis at all. Can we argue anything else? Well, I would just say it probably looks like a bird. It's never negative, and use a calculator for more detail. Okay. That should be sufficient to answer any kind of sketching question. Quotient rule and chain rule explanation. Can you give me more detail? Maybe an example of something that you'd like to see? But for quotient rule, again, I would memorize that verbal phrase, bottom times derivative of top minus top times derivative of bottom over bottom squared. You want to memorize that for the quotient rule. Oh yeah, for an exponential, sure. Let's do that on the sketch pad. You guys are asking great questions, by the way. I hope this is helpful. And if you have a follow up, like my answer doesn't make sense or something, just type it in and or ask it again, and I'll get back to it. Okay. Yeah, let's give an exponential chain rule explanation. All right. So say we have a function. That one stinks. Let's look at f of x equals e to the 3x squared. Okay. Now you're supposed to know as a fact that the derivative of e to the x is itself. It's just e to the x. Now, what the chain rule says that if you have a function and then you have another function inside of it, so basically it's not just x inside the function, you might have some g of x standing for another expression or function. Then the derivative is just the derivative of that big function with the whatever's inside of it staying as is times, and then on the outside, multiplied by the derivative of the inside function. So the key to using the chain rule is identifying what's the outside function and what's the inside function. So in the example I've drawn here, the outside function is e to the, we could say e to the x, right? Because it's really e to the x, which is composed with the inside function, which is 3x squared. We can view this whole function as 3x squared being plugged into e to the x. So when we find the derivative here, f prime of x, we have to take the derivative of the whole big function, leaving the inside part intact. That's what this says. So that's just the derivative of an e function is just itself. But then we need to multiply by the derivative within, or the derivative inside the exponent. In that case, the derivative inside is 6x. So this derivative would be e to the 3x squared times 6x. All right, I hope that makes some sense. So if you have another question on the chain rule, feel free to ask. Yeah, Joanna, great question. That's a big question. What are some functions with vertical tangent lines, if any? So the example we saw in class, I think actually Harshal just brought it up above, x to the 1/3. That has a vertical tangent line as you approach, and actually any of the odd roots are going to have the same behavior. So those are some good functions to memorize with a vertical tangent line. As far as any others, top of my head, well, yeah, we're going to look at this in the next chapter. I mean, circles, but those aren't functions. The vertical tangent lines. Those odd roots. I'll let you know if I think any others, but that's a good one. Chain rule worksheet number 4. And do we have to know the log rule? Yeah, you should know both of those rules. Just in case. Know both the e to the x and ln of x derivatives. Oh, what you don't need to know? You don't need to know I said it would be bonus. The derivative of another exponential function. 3 to the x or 4 to the x would be bonus. But you'll need to know those in the next chapters, so it doesn't hurt to learn them. All right, let's see number 4 on the chain rule worksheet. Let's find that. So this webinar, while I look for the chain rule worksheet, is brought to us by our sponsor. Fortunately, we don't have a sponsor yet. Okay, I found it. Number 4. Okay, yes, Carolyn, I can show this one. So y equals x squared plus 5 cubed times x cubed minus 1 to the fourth. Yeah, a few people asked me about this one. It's a good question. Remember, you're not responsible for simplifying any particular way unless it's a multiple choice question or if they ask you to. But this is a product rule question because we have this big function in front, call it f of x. And yes, I'm including that to the third. And this big function over here, call that g of x. And actually, Caroline, I should double check at this point. Can you see what I'm drawing? You can just type near your question. You see what I'm writing on the sketch pad? Is that visible? Is that visible? Yes. Okay. Just double checking. Okay. So product rule says we got to do the first thing times the derivative of the second plus the second thing times derivative of the first. What's the first thing? Well, we just copy it down. X squared plus 5 to the third times derivative of the second. Derivative of this whole thing. Now we have a chain rule situation because we have a parentheses to the fourth. That's like a x to the fourth function. But then inside that, we have a cubic function. So we have to take the derivative of this whole thing, we do the derivative of the big function. So we bring the 4 in front, and then it's x cubed minus 1 to the third. Lower that by 1, but then times chain rule, the derivative inside, 3x squared. And that's the first part of the product rule. Plus, I'll put a big plus sign. I'm going to go to a second line, but then we have to do the second thing times the derivative of the first. So the second thing is x cubed minus 1 to the fourth times the derivative of the first thing. Again, the big function on the outside is a cubic, it's to the third power, and then the inside function is a quadratic. So the derivative of the big function, we bring the 3 in front, lower the exponent by 1. So it's x squared plus 5 to the second, but then don't forget to multiply times the derivative within. That's how you use the chain rule. So C sketchpad for that answer. How do you explain an answer analytically when there's only a graph? Yeah, good question, Olivia. You may need additional information. The example I had for example, the one on the study guide number 1, I assumed in my equation, or I assumed in my explanation that it was like a quadratic and a cubic, but that wasn't really provided. If you have some information that you can determine what kind of function it is, then you can do some analytics that way. Um, you can also, when you're verbally discussing, let me say it this way, verbal discussions of increasing, decreasing, tangent lines, derivatives, so forth. Those are analytic discussions. So it's possible you can discuss, like we use twofold evidence in class. We use the evidence of a horizontal tangent line, which means if a function has a horizontal tangent line, then its derivative at that point, at that x value, must be 0. We also use the evidence of picking an interval. You select an interval where a function is increasing, then its derivative must have positive values on that interval. Or you could select an interval where a function is decreasing, and then its derivative must have negative values on that interval. So that would be something. Yeah. How is that different than graphic? I see your question, Julia. Yeah, that's a good question. I suppose I am. So like verbal just means talking about it. I suppose I am describing the graph as well. So this could be, it's very graphical too. The representations don't have to don't always have like strict lines. If you're talking about a graph, you're talking, so it's verbal, but you're describing aspects of the graph. So I guess that is more graphical. Um, yeah, Olivia, I guess Olivia, the real answer is you probably won't be expected to give an analytic answer unless you're given some type of information about the function. So I guess that's a better answer to your question. You can't really, unless you have some information about the function. I mean, well, but yeah, yeah. I mean, you're not going to be taking derivatives of a function unless you have information about the function. But I will say, no, these are analytic discussions. And another way you can throw the analytic in is if you're talking about the limits or differentiability. At a point, yes, you might be talking about a graph, but those are related to the analytics. But yeah, no, I'm going to bold my best answer here is this one. Yeah, Julia, that's a good follow up question because you really can't do algebra unless you have something to go on for the function. So I'm going to leave it at that. You won't be asked or forced to do algebra or an analytic approach unless you have something to go on about the function. Otherwise, if you might just have to talk about the graph, talk about differentiability, talk about limits. Okay, more questions here from Nick. How would I use a limit definition to find the derivative of something like this big messy function? Or something else you would usually use one of the rules? Well, it would take a lot of algebra. Um, Probably expand those, maybe get a polynomial, and then you'd have to plug in all the algebra. You have to plug in x plus h's wherever you saw an h. So for that reason, probably won't be asked. At least one that requires even that much. The one on the exit slip, I would say, is probably as far as I would go, and as far as the AP test would go, regarding being able to show or demonstrate a derivative with the HDEF. I think the one you've done here, Nick, was a little too cumbersome. So I don't think you'll be asked that. Oh, great question, Joanna. That one, Ocean chain rules. Mm, see a college text on real analysis. I have some in the back of the room on my bookshelf at Whippany. I think I might have some here too. But the more complicated rules, it's not that obvious. The textbook might have the product rule. I think the textbook might show the product rule, but for quotient and chain rule, that's beyond the scope of this course. But good question. But I think yeah, you can make sense of the constant rule. You can definitely prove the constant multiple rule pretty easily. Just pulling because it's a limit definition, you can pull out a constant from a limit. And then I think there's a product rule derivation in the text, but beyond that, you're not expected to know. For proving the sine and cosine derivative, we need to prove that the limit, you can assume that as a fact. It can be assumed as a fact established previously. And we can establish that numerically. Again, for those definitions, I'm sorry, to prove facts like that, you'd have to go to the epsilon delta definition of a limit that you would see in a real analysis course. But no, you can assume that as a fact. Put a graph f and f prime and vice versa from Harshal. Okay. If you want to look at a specific example, we can, but here are the general tips. You want to look, again, I mentioned this before, but I'll mention it again. You want to look for twofold evidence, Harshal. You want to look for horizontal tangents of the function, and then you want to look for intervals where the function is increasing, or intervals where the function is decreasing. And then you want to use that evidence to make your sketch. Horizontal tangents of a function imply that the derivative equals zero at that point. So you can plot some zeros. The intervals where the function is increasing implies that the derivative is positive on that interval. So you know it has to be above the axis. Interval where a function is decreasing implies that the derivative is negative on that interval. So the points have to be below the x-axis. And if it's a rough sketch, you just connect it as best as you can tell. Yes. So, Alex, part of what I just said is going to help with your question, but I like that you asked a specific one. So, let's look at that example number 3 on the exit slope. Let me just snag that. Look through my papers here. All right, here is the main idea that you gotta know to compare these. So this is when you're comparing at a specific point, f prime versus f. Here's what you want to have in your mind. F of c is the value of the function at x equals c. I'll say, to be more explicit, is the y value. That's what you want to think. It's the y coordinate of that point. F prime is the slope of the tangent line to the function at that point. So if you can remember those two ideas, that'll help you with a specific point when you're analyzing whether the derivative is greater or less than the function value. The function value is just the y value or the y coordinate, and the derivative value is the slope of the tangent line at that point. Okay. Um, all right. Oh, hello, mathematicians. Hope you're doing well. This is the office where we're tackling some calculus. Let's see if any other questions roll in. We still have about 7 minutes or so. And I will take a few more questions if you have any. I'm going to get a blank page up. Let's go back to our Google Doc. And if I didn't answer any of the other questions well, you can, re-ask it below. Just put it down at the bottom. And for anybody who's not here, I see there's about 8 of you watching. Thank you so much for coming to this webinar. Hope it's been useful for you. But if you want to share this or watch it again, it'll be posted like a few minutes after we're done. Okay. Carlin asks, when the slope of a tangent line is decreasing, does that mean it's getting closer to zero or getting more negative? Okay. The phrasing of your question is definitely tricky. I'm guessing you mean that when the slopes of the tangent lines of a function f are decreasing. I'm guessing that's what you mean, because if you mean like one literal tangent line, no, it doesn't mean getting closer to zero. Let me just answer that. In general, decreasing does not mean getting closer to zero. Decreasing means, yeah, thank you. Okay, I get your question. Decreasing in any context equals getting more negative, if you want to use that phrase, or moving in the negative direction, or decreasing, or literally getting lower in value. doesn't mean getting closer to zero. Okay? That's what decreasing means in our context. It always means getting lower in value. All right. Which trig identities would I recommend to know? Well, I mean, everybody should know, Stefan. Good question. Everybody should know the reciprocal identities. You got to know what goes with what. Everybody should be able to turn any trig expression into sines and cosines. Joanna used in class to solve a very nice problem. And Allison actually got a board point on that problem after class. But that's just a useful technique that you should always know. Everybody should always know the reciprocals. Everybody should always know how to turn a trig expression into sines and cosines. Beyond that, uh, yes, in AP Calc, there are some trig identities that they can throw at you. For example, there's a famous integral that involves the half angle formula, which we'll look at. You don't need to know it for tomorrow, just tell you that. But yes, there are some trig identities that can show up in AP Calc problems. If you look at any of the derivations of sine and cosine, you need the sum and difference formulas for derivations. Yes, Julia, that's what I mean. Yeah, that's not a very that's not sorry, I said turn any trig expression. I guess, well, yeah, I mean, if it's not already sines and cosines, it could be cosecant. So yes. Also, cosecant x equals 1 over sine x. Any of those are fair game. But some more complicated ones, yes, sum and difference for derivations, double angle and half angle, not for tomorrow. Oh, do we need to know for the trig derivative using the limit definition? I don't know which. No. No, except possible extra credit where you can. Any of the things I say, I'm not guaranteeing that they won't be needed for extra credit, but for the regular test. Yes. Is turning tan x into sine x cos x equal to turning it into secant square? Oh, um, okay. We're getting a few more questions. We got about 3 minutes left, so you can shout out any of your questions. I would say it's difficulty is subjective. It depends on your preparation. But if you know the study guide, have done all homework, have prepared, and know all your concepts, hopefully it should be a good day. There's that added pressure because it's a calculator and a non-calculator, so you gotta be really alert. Be alert from the moment it starts. Try to get as many things done as you can, and if you get stumped on one, move on, go to the next. Try to go back to it later. Is turning tan x into sine? Oh, Julia, great question. Um, so you're kind of talking towards the derivation. Maybe a quotient rule. I'm not going to give that away because it could be a potential extra credit. But yeah, you could try that yourself. Type it out, use the quotient rule, and see if you get what that is. All right. Any last minute questions? Any last minute questions? Going a few times. What section should we spend more time on? You got to know them all. Oh, I think there was a tip. Hold on. I had a tip about that. I think I had a tip. There will be a question on particle motion. Oh, yeah, Justin. Okay, I will say this. I don't want to give anybody any false or fake news here, but there's not a ton of trig derivatives in general. I think it shows up on two different questions, The 3.5, there's not a ton of that. It's more important to know the rules and the concepts, differentiability, continuity, and particle motion and all that kind of stuff. Not for the regular tests. All right. I think this was a good webinar. Hopefully, you got some of your questions answered and you can put in some good study time. I'll be here in the morning. All right, I'll be in my classroom in the morning at about 7:40. So if you want to stop in, you can ask some final questions then. Okay. Thank you, mathematicians. And I'm gonna lock the Google Doc. No, I can't lock it. But yes. Okay. Thank you for the help. Hopefully it was helpful. And I'm going to post the Google Doc and the slides and the video on Classroom. Thank you, mathematicians. And I've been trying to end this for a minute. I just can't find how to do it. Where is the live stream button? Okay, here we are. Over and out. Have a good night. This is Mr. Droza. Good luck tomorrow.